In section 12.5, we're looking at arc length and curvature. Our objectives are to find the arc length of a space curve and to find the curvature of a curve at a point on the curve. Theorem 12.6 gives you the formula that we use to find arc length of a space curve. If C is a smooth curve given by r of t, a vector valued function, equals x of ti plus y of tj plus c of tk, on an interval from a to b, then the arc length of C on the interval is equal to s. That's a lowercase s equals a definite integral from a to b of the square root of the quantity x prime of t squared plus y prime of t squared plus z prime of t squared dt. That is equal to the definite integral from a to b of the magnitude of the r prime of t dt. In this example, we're going to find the arc length of the curve given by r of t equals ti plus 4/3 t to the 3/2 j plus 1/2 t squared k from t equals 0 to t equals 2 as shown. Here we have a path in space from t equals 0 to t equals 2, and we want to find the length of that path as it's traced out. Using x of t equals t, y of t equals 4/3 t to the 3/2, and z of t equals 1/2 t squared, you can obtain x prime, y prime, and z prime. We use those to find the magnitude of the r prime of t vector. X prime of t equals 1, y prime, using the power rule, is 2t to the 1/2, and z prime is equal to t. So the arc length from t equals 0 to t equals 2 is given by a definite integral from 0 to 2 of the square root of your x prime of t plus y prime of t plus z prime of t dt. And by making the substitution, we get the definite integral from 0 to 2 of the square root of the quantity 1 plus 4t plus t squared dt. Now this involves some advanced integration technique to evaluate the definite integral. You can refer to the integration tables in Appendix B of the back of the book and see that this, when rearranged using some algebra, looks similar to Formula 26. So by using the substitution in the integration tables, we find that this can be evaluated by integrating and plugging in the upper bound and the lower bound. When you make those substitutions and subtract, you get approximately 4.816. Now this is rather tedious, so I would like to show you how you can use a graphing calculator to evaluate the definite integral to come up with the approximation of the arc length. When using a graphing calculator to evaluate a definite integral, we want to go to the original definite integral from 0 to 2 of the square root of 1 plus 4t plus t squared dt. It's not necessary to rearrange the terms so that it looks like one of the formulas in the appendix. Our first step is to, on your graphing calculator, make sure you press on and go to the home screen. You have a clear screen. I'm going to press the math button, and you can scroll down until you find the option that will allow us to integrate this function. And in this calculator on the TI-84 Plus, that's option number 9. We're going to integrate the function fnint. Now if you have an updated edition, then your definite integral is set up in a pretty easy to understand format. If you don't have the updated edition, you would enter the fnint, and then you would enter the square root of 1 plus 4t plus t squared, putting a parentheses in the correct places. Then you would do comma your variable t, comma your lower bound, comma your upper bound. It's a little bit different on the updated models, and so you would set your bounds using the arrows, and then I'm going to enter the square root of 1 plus 4t plus t squared. Now you can use the x as a variable here as well, instead of the t, as long as whatever variable is used within the integral is also used for the differential dt. So we're integrating from 0 to 2 the square root of 1 plus 4t plus t squared dt. And you can see the calculator only gives the approximation of the arc length of 4.8157. And you see that that agrees with what is shown when you do the advanced integration technique using the tables in the back of the book. For this example, we want to find the arc length of r of t equals the vector with components t and t squared for the time interval from 0 to 4. I'd like you to do this one on your own, pause the video, and then come back to compare your answers. So what I've done as a setup is I've graphed the original vector valued function of t comma t squared from the interval from 0 to 4. I adjusted my window so that I can see the time from the path from the time 0 to the time equals 4. So you can see from this path begins at the origin and moves to the location 4 comma 16. We want to find the length of that path. We are going to find you can evaluate this definite integral formula. Notice that it has a z prime of t. This is for space curves. Even though this is a curve in the plane, we can still use this formula. We can also use this formula, which is equivalent to the magnitude of r prime of t in the definite integral from a to b. So let's go ahead and find r prime of t. Given that r of t is t comma t squared, then r prime of t would be the derivative of t is 1 and the derivative of t squared is 2t. I'm going to go ahead and take the magnitude of the r prime of t vector, which would be the square root of 1 plus 4t squared. You square each of those components, add them together, then take the square root. Now I can set up the definite integral from the time interval from 0 to b of the square root of 1 plus 4t squared dt. Now you can use some advanced integration techniques to evaluate this definite integral, or what I'm going to do is go to the calculator and evaluate the definite integral to get a decimal approximation. To do that, I'm going to choose the option Math under the Math menu to integrate the function fn, I, and t. I'm going to set my lower bound and upper bound to be from 0 to 4 using the arrows. And determine an approximation of 16.8. So the arc length of the path from the point where time equals 0 to time equals 4, from the point 0, 0 to the point 416, the length of that path is approximately 16.8. It's always nice to have a graph so that you can confirm that your answer is reasonable. So about 16.8. Okay, I'd like you to try this one on your own. Find the arc length of the vector valued function r of t equals the vector with components sine t, cosine t, and t cubed for the time interval from 0 to 2. You can pause the video now, work on the solution, then come back to check your work. Okay, so we're going to go ahead and find r prime of t, take the derivative of the vector, r prime of t is equal to the vector with components. The derivative of sine is cosine of t. The derivative of cosine is negative sine t, and the derivative t cubed is 3t squared. By the way, this graph is three-dimensional helix, so I didn't go through and sketch that. But we want to find the arc length from the time equals 0 to time equals 2. I'm going to go ahead and find the magnitude of r prime of t, the square root of cosine squared t plus sine squared t plus 9t to the fourth, all under the square root. Now we can use that when we set up our definite integral from the time interval from 0 to 2 of the square root of, well, I'm going to go ahead and simplify this because I know that cosine squared t plus sine squared t is equal to 1. So it's the integral from 0 to 2 of the square root of 1 plus 9t to the fourth dt. I use a calculator to get a decimal approximation for the arc length. So when I enter this on the graphing calculator, I find that the arc length is approximately 8.6.